We said in this video we're going to look at an example, right? We're going to look at an example. So the example that we have is we have a rectangular block of mass. It is of mass equal to 10 grams that rests on a rough inclined plane. I'm going to draw the diagram. So we have a rough plane which is inclined to the horizontal at an angle theta, which is arc sine 0.05, right? 0.05. A force of 0.03 newtons acting in a direction parallel to the line of the plane of greatest slope is applied to the block so that it moves up the plane. So we are pulling this block up the plane. Let's actually start drawing it now. So this is the incline. This is the incline, right? And here we said it's inclined at an angle of arc sine 0.05. And we have this block on the inclined plane, and we are pulling that block, the block being of mass 10 grams, we are pulling it with a force of 0.03 newtons. That's what we're doing, right? That's what we're doing. We're pulling it with 0.03 newtons. But we said it's a rough plane. If it's a rough plane, it means there should be friction coming down here, right? Because we're pulling it upward. Friction is always opposite direction of motion. We're pulling it up the inclined plane, which means friction is acting down the inclined plane. Cool, that's what we know, right? So here we're saying the force is working, and then it's applied to the block so that it moves up the plane as that. When the block has traveled a distance of 110 centimeters, so which means the block has traveled a distance of 100 from its initial position, the applied force is removed. So when it's now at 110 centimeters, we remove this force. Okay, the block moves on and comes to rest again after traveling a further 25 centimeters. So what is happening here? We have a situation where, let's just say it started at the bottom here. We applied the force to when it was now at 110 centimeters. And when it was at 110 centimeters, we removed the force. The block, because of the momentum that it had, it moved a further 25 centimeters and then came to rest there. That is the situation. We pulled it, we yanked it with 0.3 newtons for a distance of 110, and then we removed the force, and because of the momentum it just moved a bit for 25 centimeters, and then it stopped there. What are we supposed to do with this information? We're supposed to calculate, this is the question, we're supposed to calculate work done by the force that we're applying, cool, to gain in potential energy, gain in PE of the block. So the block gained what potential energy, right? And then 3, this is a long example, 3, value of coefficient of friction. Value of coefficient of friction between the block and the surface of the inclined plane. We did say it's a rough surface, right? It's a rough inclined plane, so there is friction. So we can calculate the coefficient of friction. So let's see how to solve this. Okay. So for number one, right? We know that the force is equal to 0.3 newtons. And it acted for a distance of what? It acted for a distance of 110 meters. 110 meters. And it was in the same direction as the S. Same direction as S. So perfect. We can easily calculate number 1. So work is equal to F times S, which is just equal to 0.03 newtons times, what is our S? 110 centimeters, which is equal to 1.1 meters. So the work done is just going to be 0.003 newton meters or joules. That's just it. Simple like that. Done. Let's look at the gain in potential energy. So let's go back to our block. Let's look at the forces that are acting on this block, right? Forces that are acting on this block. Let me write them down. This block, of course, yes, I'm not going to use that because we want to look at forces. This block is going to have weight, which is calculated as mg. because it is in contact with a surface, there's going to be a reaction force, which always is perpendicular to the surface itself. So we have a reaction force there, right? So what is the gain in potential energy? What is the gain in potential energy? That's an interesting one, because we want, I put the block here, the force is there, but actually let me put them where they're supposed to be. Let me delete those like that. Okay, cool. So this is where we should put the forces, because we want to know when the block now comes to rest, what is the potential energy that it has gained. So here, when it's in this situation, we know that there's going to be weight of the block, which is mg, and there's going to be a reaction force which is perpendicular, so we have a reaction force, and there's no, what is the other force that is working on it? Of course, yeah, we're going to have the friction force that is going to be there. Yeah, we're going to have the friction force that is going to be there. So cool. So the friction force, yeah, the friction force could actually, I think the friction force, we're going to have the friction force actually on that side. We're going to have the friction force actually on that side. Let me write the friction force correctly. The friction force is going to be on this side, because the block wants to fall down. The block wants to come down the incline because of that's just the world, the way the world works. But if it remains stationary here, it means the friction is working in the opposite direction to it wanting to fall down. So let's just leave it like that. So it's remaining stationary there. What is the gain in potential energy? Very good question. Let's calculate that. The gain in potential energy is going to be equal to, if you know our potential energy, when we did potential energy in our previous videos, we said potential energy is equal to mg times the height above the ground. This is a very, very important point. I'm going to emphasize it, guys. This height that we're talking about is height above the ground, or height above a fixed point. What is the height above the ground for this object? The height above the ground, this is the ground. So the height above the ground is this here. That is the height above the ground. And what it means is, when you look at this, it looks like a rectangle, right? It looks like a rectangle. So which means we need to calculate this h. What is our h? And I'll tell you why I'm emphasizing this. Our h is equal to, this is the opposite side, and if it's a right angle triangle, this is going to be a right angle triangle, right? It's going to be equal to, we can use sine theta. Sine of this angle, sine theta, is going to be equal to our opposite h over our hypotenuse. So our h is equal to our hypotenuse times sine theta, which is equal to 110 plus the 25 centimeter, which is 1.35 sine theta. That is the what do you call this? That is the h. That is our h. But our theta, we're told that our theta is arc sine 0.05. So here our h is just going to be sine of arc sine 0.05. Sine of arc sine, it just falls away. So this becomes 1.35 times 0.05. This is the distance that we use. That is the height that we use. The emphasis that I wanted to make on this is, when we're doing gain in potential energy, we do not look at what it did along the inclined plane. Whatever it did going up like this, we do not care what distance it traveled here. What we care about is the distance above the ground, and it is h. So whether it traveled for 20 kilometers, we do not care. We do not care that it traveled for 20 kilometers. We're just looking at this height. That is what we're looking at. Height above the ground. I can't emphasize that enough. So many students, they make a mistake of using to say, no, the potential energy is going to be multiplied by 1.35 because it moved through 1.35. No, we're saying potential energy gained is always above the ground, or above a fixed point. So here we're going to use our h. I hope I've emphasized that enough. So this is going to be equal to our mg, which is 0.01 times 9.8 times 1.35 times 0.05, which is equal to 0.0066 joules. Perfect. That is just our potential energy there. That's how you do that. And I can't emphasize it enough, guys. H is always above a fixed point, above a height, or below a fixed point. Above or below a fixed point. It is not that inclined distance. Nope, it is not that. So now we're saying the value of coefficient of friction. So here, the work done against the frictional force, it is equal to the work done by the force. When we were doing this work, it is equal to, so let me write that down, work done against friction, it is equal to work done by the force minus the work that went to gaining pH, to gaining PE, I mean gain in PE. So yeah, this force, this thing here, when we're pulling it, right? When this object was doing work, it was doing work. One work was going towards the friction, overcoming friction. The other work was going towards gaining PE. So yeah, that's what we're basically showing here. So okay, let me write it better. Work done by force, and you see where this is coming from. Work done by force is equal to work done against friction, to fight off friction, plus the work done to gain PE, work done in gaining PE, in gaining potential energy. So the other work was converted into potential energy, the other work was done to fight off friction. That's pretty much it, right? What is the work that is done by this force? We know that the work done by the force from our point number 1 there was 0.033 joules is equal to work done against friction. What is our frictional force? Our frictional force is Fr, and Fr is calculated okay, so let's just write Fr. Let me just write Fr for now, plus our work done in gaining PE. What PE did it gain? It gained 0.0066 joules. That's what we know, right? So our work done for frictional force, it's not actually frictional force, because this so work done against friction. So let me write that. Work done against friction is then going to be equal to 0.033 joules minus 0.0066 joules. This is equal to, okay, yeah, it is equal to 0.0264 joules. So that is the work done against friction. That is the work done against friction, right? So yeah, we're going to now say, so as friction here worked. So friction, what is the work that friction was doing, right? As it was going up, what is the work done by the friction? The work done by the friction is obviously going to be the force of friction times the distance it traveled. Can you see as the body was going up, friction was doing work all this while, doing work. Friction was doing all the work up until this point. Friction was doing work all this while as we're dragging there. So what is the work done by this friction? The work done by the friction is just going to be the force of friction times the distance that it traveled, that it worked. The distance that it worked is going to be 110 plus the 25 up until that point. I think you see there, hopefully you see what I mean there. So our friction is going to be equal to, our work done by the friction is going to be force of friction. I don't know why I'm writing FR. You can write it FF, whatever it is. I'm just putting FR, friction. So it's going to be FR times 1.35 should be equal to 0.0264, right? So our force of friction, if we are going to calculate our force of friction, is now going to be equal to 0.0264 divided by 1.35 newtons. So that is our force of friction, right? So now, from an equation, it is I think we discussed this equation. Friction is always calculated by mu r. Is calculated by mu times the reaction force. What is the reaction force? If we look at this diagram here, what is the reaction force? The reaction force, because this object is not flying off the object. Can you see? This object is not flying off, that the reaction is pulling it off this inclined plane. So it means whatever is pulling it off the inclined plane is equal to whatever is pulling it onto the inclined plane. So the reaction pulling it that side should be equal to a force that is pulling it on this side for it to remain on the inclined plane. So if we resolve our forces in this direction, we're going to have reaction on this side pulling the object. And what are the forces that are pulling it on that side, on the opposite side to the reaction? It is the component of the weight. So let's resolve our component. This is an angle equal to theta. There's an angle equal to theta. So this is then going to be mg cos theta. So for it not to fly off this thingy, for it not to fly off, our reaction needs to be equal to mg cos theta. So that's what we now have there. So our friction is going to be equal to friction is going to mu mg cos theta. Mg cos theta, right? And here you can now use a calculator. You can now use a calculator to calculate what cos theta is, because we know that theta is equal to arc sine of 0.05, but it's so tiny. It's a tiny angle. You can ignore it, but you can prove it. You can prove it using the calculator. You see that therefore our frictional force that we have calculated here, our mu then is equal to F divided by mg cos theta. If you want to keep the cos theta to be accurate, you calculate your cos theta, you get it there. So this is going to be equal to 0.0264 divided by m, which is our mg. So 135 times 0.01 times 9.8. Our 135 already coming from here, which is our frictional force. You see that our mu, oh my goodness, I don't know what's going on. Yeah, our mu is going to be equal to 0.2. That is our coefficient of friction. That's our coefficient of friction. This was a really long example, but it touched on so many things. It touched on work done, it touched on potential energy gained, and we emphasized a very important point, that potential energy gained is not this work done on this incline. No, it is going to be calculated using the vertical height, height above the ground, and then we did the coefficient of friction. So in the next video we are going to quickly discuss something called conservative forces. And it's a very important concept, conservative forces. So see you in the next video.